All right, I think we are ready. We've got a little bit more on gearing to do. Got some gears here on the screen that we'll look at in a second, just for a minute to describe some things. Let's look at what's left so we have an idea. We've got today's topic with gear tooth bending stress, but using the Agma method. So last time we did a little introduction to gearing, and we didn't really talk about the gearing failure modes of any sort. So we just talked about the gears in general. Then Wednesday we'll do another Agma. So Agma, AGMA, that is the American Gear Manufacturers Association. And they have equations that are built on equations that are theoretical, but they've added a lot of factors, temperature factors and velocity factors and all these overload factors to try and make them more realistic in the way the gears actually respond to stress. And so that's what we're going to do today and Wednesday. And then on Friday, we'll wrap up, not gears. We'll try and do a few other little topics, mainly friction elements that are in your book. Your book does have a few other things in there. There's a little chapter on kind of a collection of design problems. So it goes through a double reduction gearbox design and looks at all the different little pieces that might go in there. So it's interesting. We're not going to go through that one, but it is an interesting kind of comprehensive look at all the machine element components. And then there might be a couple of others. Depending on what edition of the book you have, there might be a chapter on geometric dimensioning and tolerancing. We talked about that a little bit in the limits and fits section for shafts. But mainly on Friday, we're going to wrap up with some of the friction elements. And that's it. We'll be done. We got an exam on that Monday. And we're pretty much at the end of this thing. So let's look at this gear tooth bending stress Agma method. So before we do the Agma method, we do need to use kind of a little theoretical approach to what's going on. And it's called the Lewis bending equation. So it's a older equation that it underestimates the stress that would be in a tooth when it comes to bending, but it's what Agma is kind of built on top of. So let's get that off the screen. Let's look at these guys. If we can zoom in some to them. All right, so hopefully, we don't need that one. Hopefully you do remember how like the gear ratios work. So this one, the blue one, is a 16 tooth and a 24 tooth. So 24 to 16, that ratio is 1.5 to 1. So if I were to turn the larger one, keep it engaged there, one turn, then sure enough, the smaller one has rotated 1.5 turns. Now the arrows are pointing at each other. And that's one of the main purposes of gears, is that you can achieve these gear ratios. You can achieve similar things with like belts and pulleys. Drums could run against each other. So there are other ways to achieve this ratio. The difference with a gear is that you're pretty much assured that there's no slipping. The only way that this is going to slip is if the shaft that one of these is on is able to bend enough to where it actually moves out of the way, and then it might just barely engage, and sometimes it slips, sometimes it grabs, sometimes it slips. But assuming that your gears are well aligned, your teeth don't fail, then you can be pretty sure that you don't have any slipping between the two, the pinion and the gear. So again, in this case, the pinion, we would talk about the smaller gear being the pinion and the larger one being the gear, just to name them. There are other types of gears. These would be spur gears. So the tooth shape here is an involute shape, and it is they are spur straight cut gears, so they're not at an angle anywhere. Chapter 13 goes through several different gear tooth shapes. We're actually in 14 today, but it goes through different gear tooth shapes and even some of the ways that the shape itself is made, like fabricated. And so this is kind of your standard spur gear. There's nothing particularly fancy about the shape of the tooth except that it is involute. It is not a triangle. There's that little bit of a curve to it there. This is also involute with a little bit of undercut. So you can kind of see these teeth do mate together. But this one being so much smaller, you can kind of see how the tooth profile is a little different. Down in the base, there's this cutout part. That's the undercut. These don't need that undercut because the diameter of the gear is larger. But once you get to a certain size, a smaller and smaller size, then you're going to get more and more undercut so that the teeth can actually have a place to be. You can kind of see the blue tooth kind of goes down in that undercut area. Otherwise, there's no clearance for the point of the tooth when they're moving around. So that's just some of the things that we have to worry about. What we're going to calculate today is the bending stress. So as the teeth are turning past one another, there are two forces. One of them is a tangential force, and one of them is a radial force. I'm looking at the blue gear, for instance, but they both have these forces on them. So the tangential force is the one that as the tooth, like the tooth on the black gear interacts with the tooth on the blue gear, it's pushing past there. That tangential force is the one that's creating the torque over here. And the pressure angle, remember we discussed that there were three pressure angles that are common today: 14.5 degrees, 20 degrees, and 25 degree pressure angles. So what that determines is, well, it determines the shape of these gear teeth, but it also, the tangential force and the radial force are components, like in this case, maybe X and Y components of that pressure angle. So the pressure angle being maybe 20 degrees, 20 degrees might be more like that. You would have the tangential component being the horizontal component of that pressure angle, and the radial component being, the Y component of that pressure angle. In fact, you can see since these aren't locked in place, they can slide. If I don't hold this one in place, then you can actually see the radial component. Eventually, it will push this gear away. That's the radial component pushing the blue gear away. And that's something you have to be aware of, because the shaft that these gears are on have to react to that radial component. So too large of a radial component, and if you had like a 45 degree pressure angle with a really large radial component, you're going to have to be reinforcing the shaft that gear is on, so that you don't do this. You don't push you don't push them apart. All right, so those are just terms and things to be aware of. Let's look at the idea of the Lewis bending equation. So I'm going to let's just take this guy off, and let's see how close we can zoom in to one of these gear teeth. Let's do the ones at the top here with the arrow. I wonder if I can zoom in more. I can. Wow. All right, that's as far as I can go. All right, so this is the involute profile. And what Lewis does, or did, I don't know when Lewis bending equation was developed, but many, many years ago, what it does is it goes in and it treats this tooth as like a little tiny cantilever. And so instead of having this, this shape involute profile, it more or less treats it like a rectangle. So I'm going to try to draw something like this with a rectangle superimposed on it, and then the tangential force let's just use this one. The tangential force from the mating gear is going to be the worst possible place to apply that force would be at the very tip up here, right? Because if I'm thinking of this guy as a cantilever, then the force being applied at the very tip of it would be the worst case scenario for a bending stress down in here at the root of that bit tooth. It makes a couple of assumptions. It doesn't even acknowledge the radial force. The radial force pushing this way would actually kind of help make this a stronger gear tooth, right? Because it's going to kind of counteract some of the bending down here at the root of that tooth. But Lewis ignores the radial component. it only looks at the tangential, and it really only assumes that there's one gear tooth in contact at a time. So it is possible, like maybe right here, I haven't calculated it, but it's possible that this guy and some of this one are in contact at the same time. So you can have more than one tooth in contact between a pair of gears. Sometimes it's labeled as a fraction, like 1.2 or whatever. And that just means that on average, as these are spinning, you have one and a part of another gear tooth in contact with each other. It's not necessarily like 20% of another gear tooth. That's not what it means, but it's similar to that idea. So if you're averaged 2, then you would have always on average at least 2 teeth in contact with each other. But Lewis is thinking of only one, and it's the worst case where all of that force is, it's going to the point where, right, maybe at that one, where the force is right close to the tip. So it's going to put the tangential force right at the tip of the gear. All right, let's zoom back out, and there we go, and put together something like what we're talking about. So there's our tooth, and the worst case scenario is your book uses a W with a superscript T. I don't remember if it uses a lowercase t. I think it does. Yeah, there it is. That's the tangential force from the mating gear, and it uses that at the tip of this thing. Treats this more or less as a, some sort of little cantilevered beam here, something like that. And then it applies, now it might look more familiar if I turn it this way, and I've got a cantilever beam with a point load on the end of it. And that's what it does. It goes in and it basically solves sigma equals m times c over I. So that's a bending equation for a cantilever, or well, for a beam. Doesn't have to necessarily be a cantilever beam, but bending for a beam. And it doesn't use any of these variables. So the actual Lewis equation is, let me get it out of the book, 14.2, equation 14.2. And it is sigma equals, and then it has WT, so that's the force. And then there is a P over a F and a capital Y. So we have to go through what these actually mean. So WT is the tangential force, so that one's straightforward enough. P, we did talk about that last time. That is the diametral pitch. So let's fill these in. WT equals tangential force. P is diametral pitch. So the diametral pitch, that is how many teeth are there per inch of, well, I'm going around this way. That would be circumferential pitch. Diametral pitch would be how many teeth are there per inch of diameter. That's where the diametral part comes in. So in this case, I don't know what the diametral pitch is, but the diameter of this thing is like, well, I don't have a ruler. Something like somewhere around 2 inches. I don't know exactly. The diametral pitch is not to the tip. It's kind of that contact point for the pressure angle. And so it's not the actual part, but it's somewhere around 2 inches of diameter, and then we've got 16 teeth. So I have 16 teeth per 2 inches of diameter, so I'd have 8 teeth per 1 inch of diameter. So in this particular gear, I'd have roughly an 8 for diametral pitch. F is face width. So that's, how much face do I have here that is making contact? So if this was a really narrow gear, then obviously the teeth are going to be narrow, and they would be more susceptible to a bending stress failure. And if they're really wide, you know, I've got a really wide tooth over here, then that's going to create less bending stress. And this face width is in the denominator of this equation. Y is something totally different. Y basically takes on the role of C and I in my original bending stress equation. I guess the face width does also. But this is the Lewis form factor. And it is, let's see if I can get a chart up here. I opened one up earlier. Let's find it again. There? Yeah. So there's a chart in your book. It didn't give me the, table 14.2 down at the bottom. And this number of teeth is the Lewis form factor. So if this was a 16-tooth gear, then the Lewis form factor would just be this number, 0.296. There is an equation for Lewis form factor, but there's also this chart. Equation, I don't know, 14.3 maybe, I think is the, yes, equation 14.3 is the equation for the Lewis form factor. So what we could do, why don't we go into MathCAD and set up, not these gears, but another set of gears, and run through how we would calculate the bending stress from a Lewis bending stress point of view. So let's get MathCAD open. Let's see, let's move that out of the way. And I think MathCAD is hiding back here somewhere. There it is. All right, dogs are barking as usual. Here are our pinion and our gear. They're a little bit fuzzy, but all we need is the picture of them. You might be able to see this little red line on here. That's the pitch line. You might also be able to see these dots. Those aren't really important for anything. There are labels on here. So the blue tooth has the blue gear has 30 teeth. The gray, I guess, pinion has 12 teeth. They have diametral pitch of 6 is what they're set at, and a 20-degree pressure angle. So we'll plug those things in as we need them. Let's put our equation in, Lewis equation that we're trying to solve. Now your book also does go and add another kind of modifier to Lewis, which is a velocity factor. So the faster these gears are spinning, the more load they have to endure. And so there is this velocity factor that can be added. We're not going to add that part to this. Sigma. This is going to be the bending stress at the root of the gear tooth. Here we're just going to define it. W. Now, I'm having to trick MathCAD, so I've got this T equals 1. That is because the units, or not the units, the variable that your book uses for that tangential force, I don't even know if you picked up on it, but when I was writing it, the T was actually a subscript, but it's not an exponent, it's just a subscript. So I'm just saying WT, but T is just 1. So that's how I'm getting MathCAD to agree with me here, that that's not a, well, it does think it's an exponent, it's just an exponent of 1. But it's just a superscript in your text. It doesn't mean anything, it's just tangential. All right, so we have to come up with these values. So the diametral pitch is just written on the gears here, P equals 6. So we can get that one. We'll do the same thing where it's teeth per inch, but teeth aren't actual units. So we'll just make MathCAD think that it's just a 1. Let's see, face width, we can define that. So remember, the face width is how wide are the teeth on the gear. So you might have a hub, kind of see this little area over here that sticks out. That's not the face width. The face width is how wide are the teeth. So I'm going to make these a 1/2 inch wide. So that would just be something you measure, or you know, or you're given, or maybe that's the thing you're solving for. That's one of the easier variables to modify if you come out with a gear that is the right shape. It has the right gear ratios with the gears that it mates with, but it's not strong enough. This face width is the easiest thing to modify. Just make it thicker. You know, instead of trying to put more teeth in there or run at a different speed or whatever, just make the gear teeth wider, and that will reduce the stress on the tooth. So this is one of your main design variables, and for us, we're just setting it at 1/2 inch. Y, that's an easy enough one. That's the Lewis form factor. Now, we do have to decide, are we talking about the pinion or the gear? Most of the time, you're going to be dealing with the pinion. But you could easily also operate on the gear. Well, let's look at the Lewis form factor for a reason why. So these have teeth of 12 and 30. So that's not it. Where'd it go? Oh, I pulled it out of the way. Yeah, it's over here. 12 has a form factor of 0.245. This number is in the denominator of the bending stress equation. So 0.245. The other one was, I think, 30. 0.359. So the larger number of teeth will put a larger number in the denominator of the stress equation. So it will lower the stress. There'll be a lower stress, bending stress on the gear tooth with more teeth on it. So you're going to be working it with the pinion, the smaller gear. So we're going to put 0.245, just reading it off of here, as our form factor. Actually, let's leave that. We'll keep coming back to that. So let's leave that more or less there. Let's do this. All right, so y equals 0.245 from the table. So we need the tangential force. So I'm going to get this one in a way. So we have done here and there, maybe even in the shaft lectures, a couple of different places, we've done a couple of things, and we've talked about this pressure angle. You just take the horizontal component to get the tangential force. And I do have the pressure angle. It's 20 degrees. But we're going to get this one from a different route this time. So let's figure out how much power we're dealing with. And from that, let's figure out what the tangential force was going to be. So that's a little bit different than the way we've done it before. So it's just a different process. So I've got to set up some more given situations. So let's say the torque on the gear. So the gear is the blue one. And I'm going to define this 125 foot-pounds. So it's given. Let's also say that the omega for the pinion, oops, I didn't get the subscript in there, did I? Is equal to, so this is the speed of the pinion, 100 RPM. So those are just given values that we are designing for or that we've set up already. And now, well, in the pressure angle, I meant to find out what variable gives me the symbol for pressure angle, and I don't know what it is. I could just go through all of these until I find, oh, that's going to be pi. Oh my goodness, which one? Oh, it's J. All right. Or that's going to be closest that I have to what I need. So that's the pressure angle, 20 degrees. All right. So our gear ratio can help us figure out either the gear ratio or just the ratio of the diameter. So we could put the diameters in here also. So the diameter of the gear, I'm using the uppercase G to mean the gear, the blue one. It's written on there at 5 inches. And the diameter of the pinion is written on it. You may not can see it, but it's 2 inches. So you can either use these diameters or you can use the number of teeth. Oh, got part of a comment, but I don't know if it's all there or not. Not sure. We'll check on the chat and see if the rest of the comment comes through. Right now, that doesn't have any more. All right, so we have diameter of the gear, diameter of the pinion. We have, and these are all given values. So none of these we've calculated. Here we can calculate. Oh, F is perfect. Thank you. It's F. If I can type the letters. There we go. Oh, that kind of makes sense since it starts with the F sound. All right, great. I guess I was just going across the keyboard and didn't get the F. I found the other symbol that looked similar. Great. All right. Diameter of the gear, diameter of the pinion. And now let's calculate some of these other values. So these are all given. I don't want to write, actually I can write it this way. Given is a keyword in MathCAD, so I didn't want to write it as a variable, but we can write it as in quotation marks and it's just text. All right, let's calculate the torque on the pinion. So this should be a pretty basic calculation, just using either the diameters, so 5 to 2, or using the number of teeth. I didn't actually put the number of teeth in here, but we could also put those. They are also given. I'm not going to use them, but just for completeness, we can have them in here. So there are 30. We do have our teeth variable set up, so we can put teeth in there. And pinion is 12. Remember, you can't use teeth as a unit unless you do something like this earlier where you just set it equal to 1. All right. Torque on the pinion is the ratio of the diameter of the pinion to the diameter of the gear times the torque of the gear. And it came out in joules, so let's put it in foot-pounds since that's what our other stuff is in. 50. And, you know, we could have sorted this out ourselves just with algebra. We could also do a similar thing with the speed. Omega of the gear, we have omega of the pinion. So omega of the gear would equal the diameter of the pinion over the diameter of the gear times the omega of the pinion. Oh, I just typed W, I didn't do the, there we go. I don't like the way the subscripts work in this version of MathCAD. Let's put it in RPM though. 40 RPM. So we could have, now we can calculate the power of either of these. They'd be the same number. But if you remember, in general, power equals torque. Oh, wow. Power equals, why can I not get that to work? There we go. Torque times omega. That's the generic form of power. And we have torque of the pinion and we have the omega of the pinion, or we have the torque of the gear up here and the omega of the gear. So we can use either set and get a power number. So power for us is, now we do have to be careful, right? Because we have P over here, meaning the diametral pitch. So if I have P over here, it's going to get confused. I'm going to call this one power. This one, where I use the symbolic equal sign, it doesn't matter, but we could call it power also, just in case. All right, so power equals, let's just do the pinion. Torque of the pinion times the omega of the pinion. Now, if you're doing this by hand, you couldn't just multiply, like my torque is in foot-pounds and my speed is in RPM. I couldn't multiply foot-pounds times RPM and get anything meaningful. So you do have to handle the units yourself, but in MathCAD's handling the units for me. And it's going to put watts. Let's say that we want it in horsepower. So almost 1 horsepower. And if we did the torque and omega of the gear, we'd also get 0.952 horsepower. We're assuming, which is not a correct assumption, but we are assuming that the torque transfer from one to the other is 100%. But there are losses. There are power losses on these transfers between gears. So you're not going to get 100% transfer of power. Right now, we're taking everything as the most conservative possible approach. And the pinion does have to deliver that power. It just isn't all going into the gear. Some of it's going into the lubricant around the gears, heating that up. So the power loss is not all being transferred, or the power is not all being transferred out of the system as useful power, but it's all going somewhere. So the pinion does have to deal with all this power. So we're going to take the most conservative approach and assume that the pinion has to deal with all this power. So what I want to do with that is I want to calculate the pitch line velocity. I could have started this already, but I went ahead and did the power part. So the pitch line velocity is, we can look at this red circle, the red dot on the circle, and that is spinning around. It's spinning around in a circle, but it has some velocity. Now, normally we might think of that as like an angular velocity, but we're going to think of it as a pitch line velocity. So how fast is it going around in this circle in more, not angular units, but in distance units. So that's why we call it the pitch line velocity. So it's like a line linear velocity, but it's around this circle, the pitch circle. So we're just going to give it a variable of v. We need to know how fast the pinion is spinning, so that's going to be omega p. Oops. We already have that set up here. That was actually one of our givens, 100 RPM. Times. Now there's a couple of ways we can do this here. We want to multiply times the circumference. So our circumference of the pitch line, so the little red, very faint red circle here. And one thing we could do is we have the number of teeth on the pinion. So that's 12 teeth. And we have the diametral pitch. Did we ever type that in? Yeah, we wrote it as P over here. So in P, number of teeth over pitch teeth per inch, give us the inches of the diameter, basically. And then if I multiply that times the pitch diameter, pi, I will have the circumference. So if I had, now in this case, I actually have the diameter of the pinion as just 2 inches. Or we could calculate it if you don't have the diameter given. So I did this version right here that calculates the diameter based on the number of teeth and the pitch, diametral pitch. You do have to make sure that your pitch is the diametral pitch and not the circumferential pitch. If I had the circumferential pitch, I could just use that number times the number, or divide the number of teeth by the circumferential pitch, and that number would be the circumference. All right, so this is meters per second. Let's put it in, I don't know, feet per minute. That seems like an odd set of units to use, but the equations that we're going to use later specify feet per minute. At least one of them does. So feet per minute is what we're dealing with. Now, so here we had power is torque times omega. So that's when you have this rotational power delivery. But you could also have power equals force times velocity. Velocity is right here. We just calculated it. It's actually 330 feet per minute. Power, it's the same amount of power, the 0.952 horsepower. And this force is the WT. So what we can do at this point is we go over here again. WT equals, why are we not sure? Oh, will it not let me? Oh, wow, it won't let me do that. Okay, so we're going to have to do W subscript T, because it won't let me set W with the exponent T except in the symbolic equations. It'll let me put it there, and it's on the right-hand side, but it won't let me put it over here on the left-hand side of the equation. MathCAD won't. So this W subscript T is how I'm going to get around that. Instead of, your book is going to use a superscript T. All right, so we'll just make a mental note that W subscript T is the same as W superscript T. MathCAD just doesn't like it. All right, so using this, WT is the force, so it's just power over velocity. So I have a power divided by, I call it velocity V, and there will be, I put it in pound force, 95 pounds is the tangential force on this gear tooth. We're going to put that tangential force at the very peak of the gear tooth and calculate the bending stress using the Lewis equation. So let's actually just copy this equation, paste it, change that out to a evaluation, or well, a definition, and then evaluate it. Get some weird units here. Let's see if we can get KSI out of, oh, without that. Why is it? Oh, because I've got the WT part in there. Let's change this to be the superscript T. Get rid of that. There we go. 5 KSI. Now this is, it could be modified more. Like I said, with the velocity factor, there's a KV that can bump this up based on how fast we're spinning the gears, and a couple other factors like what shape are the gears and things like that, the gear teeth. But still, it's not going to multiply it, multiple times. It's going to be a factor of 1 point something. And so you could be pretty sure that 5 KSI for most any kind of metal you're going to make a gear from is plenty factor of safety against bending stress. So Lewis, it doesn't give you an accurate number, but it does give you are you close number. So for instance, if this number had come out to be 46.7 KSI, now you're getting a little bit close to yielding stress numbers, and the fact that this Lewis equation isn't particularly accurate, you'd have to wonder. If it came out to 467 KSI, then you know that, yeah, there's no way that I'm going to get that kind of strength out of a metal gear. So I would know that I have to redesign something, and usually that means redesigning the face width. It's the simplest one. But 4.6, you're pretty sure that that's not going to fail any kind of metal gear. But if you want to know more accurate, that's when you go to Agma. All right, and I think we certainly have time to start Agma. We may not get all the way through it. It's a pretty lengthy process, but let's go over to Agma. Agma, again, is the American Gear Manufacturers Association. Wow, I spelled that. There we go. So it's Agma. And what Agma does is it takes this equation, basically, and it adds a lot of multipliers. So it's similar to when you do it in modified endurance limit. It's similar to that, where you take a base number and then you modify that number based on all these conditions that might occur. So Agma does the same type of thing. So it's going to give us a number, a stress number, like this one, but it's going to be a totally different number, and it's not an actual stress that you could compare to a strength that you would look up in a book. So what you do is you calculate the Agma bending stress and you compare it to the Agma bending strength. So you actually have to calculate Agma 2 times for the bending failure. Once to calculate the stress, the Agma stress, and then again to calculate the Agma strength for that gear. And then there's a whole nother type of failure that Agma looks at that we haven't even talked about. We'll do that on Wednesday, but the contact point between the gear teeth. This contact point is over and over cycling, and so there's a contact stress that has to be calculated. It does the same way, where you calculate the Agma contact stress and compare it to the Agma contact strength. We're definitely not going to get to that today, but we should be able to get through the Agma bending stress. All right, let's get our equation written down. Let's start a new page. In fact, let's get this guy on another page too. All right, let's start down here. So Agma, now your book just uses sigma, but I'm going to put a subscript Agma on it. If I can type a subscript Agma. There we go. Just because it's not a sigma stress that you've been using, it really is specific to Agma. All right, so W, again, I will use the superscript here, but only because I'm in the symbolic equals. So there's the tangential force. That number we already have. That's the exact same number we just used here. So that's the same. WT times KO, that's going to be an overload factor that we can look up. KV is a dynamic factor. Now this KV, a similar one does exist for Lewis. So that part of Lewis can be modified to make this number a little more accurate by multiplying by KV. And that's talking about how fast the gears are spinning and how well they're made. The quality of them would affect that. KS, this one is a size factor sort of thing. It's optional. So Agma, the way it's set up is it kind of future proofs itself so that they know that there's an effect. They just haven't sorted out the exact numbers to put for that effect. So some of these are going to be optional, and we're just going to fill in a 1 because we don't know. Now, I've got the 10th edition of this book, which was printed several years ago, and I didn't go and check the current Agma setup. If you go to the American Gear Manufacturers Association, you will find the most recent data on some of these factors. So there could be more guidance currently, depending on when you're trying to solve this Agma equation, and you would need to go directly to the American Gear Manufacturers Association to get those numbers and those charts. Multiply times P. Now they use a P sub D. We just use P up here. It's the same thing. That is the dimetral pitch. They just specify that it is dimetral with the subscript D. That number is over F, which is the face width. We have that already. We used 1/2 inch. Km. Km is a load distribution factor. It's actually going to take us a long time to calculate that one. We'll get to it in a minute. KB, not KB like we used with the springs, the Bergstrasser. It's a different KB. What is it called? It is the rim thickness factor. So that's a relatively easy one to deal with. We'll deal with it in a minute, at the end anyway. Over J, J is similar. It is a geometry form factor, so it's similar to the Lewis form factor. It's not the same number at all, but it's kind of the same thing. All right, so some of these we have. The others we need to go and figure out. All right, so first of all, K, there we go, K overload. Let's see if I can find the little chart for overload. Well, we can go through some of these equations while we are looking. There's that KV applied to the Lewis form factor. There's the Agma bending stress. Now, notice I am using US units. They do have a separate equation if you're using the SI units, and you'll notice that some of these variables are slightly different. Like instead of J, they have Y sub J, so that when you grab the number out of a chart or a graph or whatever, it has the right units in it. So if you are using SI units, then you do need to be over in this version of the equation versus the US unit version of the equation. There's the one for contact. We'll get to that later. Well, maybe I don't see the overload looking through. We'll get to some of these. There's the dynamic factor. Here's the overload factor. It's just in a little table. I don't even know if your book lists it as a table necessarily, or if it's just embedded in the text. I don't remember. But this is what it tells you. So the overload factor is some gears have to deal with shock. Some of them are smooth running, uniform. And so you've kind of got this chart here that is a matrix of power source and what's being driven. Now, in our case, I didn't tell us anything about the pinion or the gear, what they're actually connected to. So we're just going to go with a uniform power source driving a uniform load. So that gives us a overload factor of 1. But you can see this thing can get up to 2.25 if you have the power source being a kind of a medium shock level and the load being a heavy shock level on the load. So a lot of like startup and stopping or just jerking around on whatever the loads are. And so it can be a significant factor. We're going to be with just 1. So that one's simple enough. We just go to the table like that. I'll skim through the book real quick and see if I can see it in there, so I can tell you what page it might be on, but I don't remember offhand. Yeah, so here's what your book... I don't know how you're supposed to know these numbers otherwise, though. Oh, see, figures 14.7. Okay, that's the elastic coefficient. Yeah, I don't see, that doesn't actually help me. But it is on page 750 that it mentions the overload factor. And it gives a reference for where you can go look up numbers like I showed you on the screen there. But since we don't have any indication that this has a overload situation, this heavy shock or medium shock, we're going to go with K naught equal to 1. KV is the next one. So now we've got WT, we've got overload. Let's do dynamic factor. Maybe we can label these so that we don't forget. This next one will be dynamic factor. All right, so dynamic factor is KV. It is not quite as simple. Let's go find it in our chart here. Here it is. There are two equations again. So there's that feet per minute that we had as oddball units before for the velocity. It's because in this equation, the V is expected to be in feet per minute. If you're using the SI version, again, it has the two different versions, then velocities in meters per second. So how this one works is you have these A and B parameters that B is based on this QV. QV is a quality value. Also, by the way, there is a chart where you can just look up the dynamic factor off of a chart and different traces on it. We're going to use the equation though. We'll see if the chart will help us, but remember our velocity was something like 300 or so. It's going to be way down here. It's going to be hard to read. So we're going to use the actual equation. So this QV is, oh, you look at this. There are 5, 6, 7, 8. I think it actually goes up to maybe 11 or 12. At some point at the very high end, it just becomes very accurate gearing. It could go lower than 5, but those are really poorly made gears. So quality value of 5 is the poorest made that is kind of still considered something that you would buy somewhere. I guess it could go lower than that though, for really poorly made gears. So the QV is the quality. We're going to go with the lowest one. So we're going to go with the shabbiest gears we can get, and say that QV is 5. So we take QV of 5 into here, calculate B. We take B into this equation, calculate A. Then we take both A and B, put them in here, and calculate KV. So that's the sequence of events that we're going to do. So the first one was B. Well, first one is actually QV. QV is 5 for us, and we just decided that. That's the lowest quality rating that we could pick. All right, B, based on that, is 0.25 times 12 minus your QV. And that 12 minus QV term is raised to the 2/3 power. That gives us a value for B, 0.915. You use that value to calculate A, 50 plus 56 times 1 minus B. That gives us, that doesn't give us that. Oh yeah, it does, 54.77. All right, now I take A and B, plug them into the correct version of KV. Let's see if we can get this one right. A, it's going to give me an error. We'll fix it in a minute. Plus the square root of V, which has to be in feet per minute, over A. All of that, well, not all of that, all of that raised to the B. Now it's going to give me a really, like you can't calculate it. That's because this is a MathCAD thing. So the V is feet per minute somewhere. Here it is. Or it's a velocity. It has units of velocity. And A and B do not have units at all. So it can't add a unitless thing to something that does have units. So what I'm going to do is I'm going to divide feet per minute. I do need to divide by feet per minute here instead of something like inches per second or whatever, because that is the number that this equation expects, or the unit that this equation expects velocity to be in. So now it'll solve it, and I get 1.3 for kV. So we have our dynamic factor. Ks, this one is the size factor, and it's optional, and we are just going to put 1. Let's see if I have a chart pulled up about Ks. I don't even know if I have one. I don't think I do. Surface, KV, J. Yeah, I don't even think I have one for Ks pulled up. So it is an optional size factor. It's one of the ones that are kind of future-proofing the thing. Once there's more data, there would be a better way to calculate or put some number in for the size factor. This is sort of trying to take into account the fatigue, kind of the same size factor for a shaft or whatever, where if there's more of the material, there's more chance of an error in the material. But there's no data currently, at least of the 10th edition book, to put a different number in here. So we're going to put 1. Now we are at, so we got that one. We already have our, we don't have a PD variable, so let's do that. It is just what we called P. So it's the diametral pitch. So we took care of that. We already have a face width. So Km, this one's actually a lengthy one. Let's do it. Km, let's see if I have a picture of that. Hey, there was a Ks. So there is an equation you can use for Ks, where you're basically taking the method from chapter 6, and just finding the KB and doing the reciprocal of it. So you could apparently use that process. We're just going to stick with the 1. Load distribution factor. I'm looking for, here it is. So Km is all of this. So to calculate Km, I need all of these other little pieces over here. And first, let's put our Km equation in MathCAD, I guess. Let's do that first. Km, we'll do it symbolically, equals 1 plus CMC plus CPF times CPM and plus CMA times CE. All right, so we got to get all of these things sorted out. So let's go back over to this. So CMC, the first one of these, well, 1 plus, we have 2 options, 1 or 0.8. And it's talking about crowned versus uncrowned teeth. Well, I pointed to the wrong ones there. Uncrowned versus crowned. And what this means is, we'll have to maybe draw a picture. So we have uncrowned teeth on this. Let's get some blank page. If we had a gear tooth here, I'm going to draw the gear teeth as a rectangle just to make the crowned part easier to draw. So there's our gear tooth, kind of like we had here, that rectangle. And it has some face width into the page. There's a fillet down here. Like that. So that's uncrowned. So crowned is like this. So hopefully you can see I didn't just accidentally draw this line curved. That's the crown. So the idea is that instead of this perfectly flat, surface on the face here for the gear or the pinion to mate with, I have a little bit of a crown so that if I'm a little bit crooked on mating these things, I still have some good contact between the two gear teeth. So I can have a little bit of misalignment, not as much as I'm showing here. I'm just trying to exaggerate it. So not as much as this twisting, but you can have some of that kind of twisting and still get some good contact. Where if these were perfectly flat and I twist them, there's going to be a single point of contact. So the crowned gears have a better ability to handle misalignment, but they're harder to make because now each one of these teeth have to be crowned, and so somehow you have to get that crown made on the surface of this tooth, so you can't just like broach across it to create the teeth. So that's crowned versus this is crowned, this is uncrowned. All right, so we're going to have, since we have the quality 5 gears, I'm going to pretty much have to assume that we have the uncrowned teeth, because you wouldn't go and crown the really cheap gears. So that gives us a CMC of 1. All right. The next one is, and I don't know what the names of MC and PF, I don't know what the subscripts are actually, why is MC stand for crowned or uncrowned? I don't know. So PF, that's the next one in our list here. So we have our face width, which we have built in, and we have D, which is the diameter of the pinion or the gear. We're talking about the pinion in our case, so it'll be D sub P for us, the diameter of the pinion. And our face width is less than 1 inch, so we need this first equation. So that's CPF is F, face width, over 10 times the diameter of the pinion. That quantity minus 0.025. Now we're going to get we get essentially 0, right? Some number times 10 to the negative 18th. So we pretty much get 0. So what it tells us to do, and if we put a 0 in here, basically this whole thing just becomes 1. So, well, no, because this could be not 0 over here, but this part becomes 0 plus whatever that is. So who knows? But it does give us a note. In your book, it's given the note. In this chart I have, it doesn't actually give it, but let's find it over here. Let's see, here we go. No, that's it's right here. So here's the equation we're using. And then down here it says, note that for values of F over D times diameter of the pinion less than 0.05, just make that whole term, so this whole term, 0.05. So we're going to do that. So basically, let's copy this thing. And let's make this term here 0.05. And now we get 0.025 for PF. All right, PM. Well, I don't have a picture for PM. There it is. It's on the next page. So this is how is the gear mounted onto a shaft and the shaft supported. So I've got this picture here. Many times with gears, not 100% of the time, but most of the time, the gear is mounted between 2 bearings somewhere. And PM is it straddle mounted with on which side of the gear, which side of the center rather. So this is the center line of the gear. There's one bearing, there's the other bearing, the shaft is through the middle, there's the center, and one for straddle mounted pinion, which we're dealing with, where S1 over S, so S1 is the offset of mount and S is the total span, less than 0.175, and 1.1 if this ratio, basically how far off center is it. So if it's close to center, then we use 1. If the gear is kind of off to one side of the center of this span between the 2 supporting bearings, then I use 1.1. This doesn't even have a setting where the gear is actually on a cantilevered shaft, which can happen, but you have to be very certain that you don't have a lot of deflection in that shaft. So it's assuming that there's a straddle mounted, meaning that the 2 supports are on either side of the gear. All right, so we're going to say that it's in close to the middle, and we're just going to use 1. Okay, now we need CMA. Let's look at that one. There's E. Where's MA? There it is. All right, so CMA. We have another set of A, B, and C coefficients. These are not the same A, B, or A and B that we had for the velocity dynamic factor. These are related to what sort of enclosure are we dealing with here around our gearing. So is it just open gearing? We are using the quality 5, the uncrowned, so we got everything else kind of cheap, but open gearing is usually not good. It's dangerous. You have open gears running out in the open. Harder to lubricate. Grit and all sort of debris can get in there and kind of ruin your gear teeth. So open gearing is not common. But so we're not going to go that far. We're going to go with commercial enclosed units. So we're going to use the A, B, and C in this equation. F is face width for commercial. And then it gets, there's precision, and then there's this super precision type stuff. That definitely doesn't fit our narrative with the quality 5 gears that we're using. So we're going to go with commercial enclosed, not totally out in the open. So A, B, and C are here. We plug them into this equation, 1434, and calculate CMA. I want to get done. We're close to done. CMA. I want to get this complete before we run out of time, but hopefully we can do that. Oh, actually, well, we can go ahead and write A plus B times the face width. Now, this is another one where A, B, and C don't have units, so I need to divide the units out of the face width. Plus C times F over inches to divide the units out squared. But we don't have A, B, or C, so we gotta put those in. Let's see if we can put them in right here. A from our chart is 0.127. B is 0.0158. And C is negative 0.930 times 10 to the negative 4th. And now we have a CMA number. 0.135. I think we're almost done. We need CE. Yeah, I saw it in here. There it is. So we can either have 0.8 for gearing that's adjusted at assembly. So basically, how well aligned are your pinion and gear? 1 for all other conditions. 0.8 if you've done a lot of careful alignment. We have not done careful alignment with our gear setup, so we're just going to do 1. So that one we can just go down here and CE equals 1. We have all of these now, and we can set this equal. And oh, I don't have FMC. But that's just let me check. Let me make sure. Oh, because I typed it wrong. That should be CMC. Like I didn't know what that variable was. I'm messing up my whole equation. It's 1 plus CMC. There we go. And it comes out to 1.16. All of that to get this extra 16% in there. All right. Now, I think, do we have them all? No, we don't have KB or J. We have time to get those, though. All right, so KB is, it's going to be 1, so I'll go ahead and put it in. This is the rim thickness. So let's see if we can find, here it is way over here. So the rim thickness, first your gear has to have, you have to know if it has a rim or if it's a solid gear. So the ones that I've been using, these do have a rim. They have a weird like set of spokes inside here, but it's not solid. It's not a solid filled in blank like you just took a flat sheet of metal and cut the gear teeth in it. So this one does have a rim, and you can see the rim is right here. So if this rim thickness is different from, there's holes in here, there's spokes in here, or maybe it's just inset and it's not as thick, it's solid but thinner in this area and thicker out here, that means it has a rim. And then you go figure out what this rim thickness ratio is with this equation. Our gears are not these style. We're just using flat gear blanks with teeth on them. So there's no hub really. There's no spokes. There are no inset center part. Nothing like that. And so we just use the value of 1. But they have a chart and an equation. When this ratio of rim to thickness is not, or it's less than 1.2, then you could have some factor here that gives you a larger rim thickness ratio. We're just going to use 1 in our case. And then that leaves us with our geometry factor. So that one is, no, that's Y. Where's the picture for it? It's way up here, actually. Spur gear geometry factor. All right, so this is a chart for spur gears. I don't think there's an equation. Well, there is an equation for converting it, but there's also this chart. In this case, we're going to use the chart. All right, so what you have is on the x-axis, you have the number of teeth for which geometry factor is desired. Ours is 12. The Pinion had 12 teeth. And then on the other axis, you have number of teeth for the mating gear. So there's not a 30, there's a 35 though. And then you have all these traces, and the idea is that you intersect the 12 with, and actually all of these, no matter what the other tooth is, 30 teeth or 1,000 teeth, at 12, they all point to this one number. So I don't have to do anything other than get this 0.21 number as our J value. But let's just momentarily pretend we have different numbers on our pinion and our gear. Let's say our pinion is 24. So we're on this line right here now. And let's say, in fact, I probably can draw a line there. So there's 24. Let's make that a big yellow line. So there's our pinion teeth. And let's say that we have 35 on our gear. We have two options at that point. We have the option here, down here, that we're taking the most conservative approach where the load is applied at the tip. That's kind of what we did with the Lewis equation. So we could take this option, and it doesn't matter how many teeth are on the gear, just how many are on the pinion, and we get a 0.25 as our geometry factor. Or we can say, well, a little more realistic and less conservative would be we actually go and find the number of teeth on the gear. Let's say it's 35. And we intersect these lines, which end up right here, which is going to give us a 0.355, I would say, for our geometry factor. So that's how you can use this. Like I said, there is an equation. You can actually calculate it if you want to. But this is simpler because you have the different options of do you want to do the worst case scenario? Do you want to break it out to which one of these gear teeth numbers are you dealing with, or whatever. In our case, we're actually over here at 12. So our line is over here, and it just, it intersects with all the numbers of mating teeth at 0.21. So that's for J. J equals 0.21. At that point, we could go grab our Agma equation. We could set it equal. I remember I have to change this WT because MathCAD doesn't like this superscript up there. Oh, actually it would, but I have it less in that on that side. It just won't let it work on this side. Let's see what this equals in KSI. So it does give you units like PSI or KSI or whatever. 8 KSI. The only problem is you can't take that 8 and compare it to just the strength of the metal. You actually have to compare it to the Agma strength equation, which I'm scrolling through to see if I can find it. Is this it? No, well, that's the safety factor, but I guess we'll use that. Yeah, that's what we'll use. So we can solve for the safety factor. Now they have these in two different forms here because I have bending strength on one and I have contact strength on the other. So there is a fully corrected Agma bending strength and a fully corrected Agma contact strength. And this equation kind of builds those in. And this bending stress that they have listed as sigma, that's the sigma Agma that we just calculated. So we can use this equation to figure out our factor of safety. So basically this numerator is the Agma bending strength. So it's got a couple of terms in it that we don't have values for. SF, we'll go ahead and just do it this way. ST times YN, that's capital N, over KR times KT. Oh, well, yeah, I'm writing it similar to the way they had it written, but they do have it written slightly differently. Sigma Agma. All right, so let's start filling in the blanks here, and hopefully we get it done in time. ST. So this is a strength based on the hardness of the material, of the pinion material. Usually the pinion is a harder material than the gear. And if there's even, so this is just an aside effect here, but the pinion being harder than the gear, if it's the ratio of those hardness is really great, then the gear can actually undergo work hardening as it's being used. What we're going to do with this is we have a chart, not that chart, this one. Figure 14.2, and there you have to be careful because there are 4-ish of these charts that look like this one, so you have to make sure you're actually getting the right thing, the right units, and the right materials. So we're just going to go with a grade 1, and we're going to say our hardness is 250, so it's a nice even number here. So we'll just plug those numbers in over here. We can't actually get ST just yet. So our hardness is going to be 250. And then if you noticed, there's an equation, and we're grade 1 instead of grade 2. There's an equation here, or we could try and read 250. It's going to give us 32 something. But there's an equation that we can actually use to calculate that ST value once we have the hardness. So ST from the equation is 77.3 times our hardness plus, and we've got to get some units on here. These units will end up being PSI, and this is plus 12,800 PSI, and that's from the chart. It actually has that unit on there. So I need to put units because I don't have units on either of these other numbers. So we're just going to kind of cheat it. And then this will give us, let's put it in KSI, 30, and that's what it looked like, 32 KSI. We just get the 0.125. All right, we have the ST number now. YN is related to how many cycles. So there's a chart and an equation. Looking for it. This one. So the stress cycle factor, figure 14.14. So Agma is based on 10 to the 7th cycles. Just so that we're different and we can use the chart, let's say that we want to do 10 to the 8th cycles. So 10 to the 8th is over here. And there are these different material properties, different hardnesses, you know, nitrided, case hardened type different things. And so there are different traces on the lower number of cycles. Over here, everything at the higher number of cycles that we want to design for are kind of lumped together into a range. And the range has a bottom line and a top line, both with an equation. The bottom one, so the YN is in the numerator here of a safety factor. So the larger number will give us a larger factor of safety. We're going to take the more conservative approach and put the smaller number so that we get a smaller factor of safety. So since there is a range here, we're going to take the more conservative approach to that, which means using the one that's going to generate a smaller number for yn. So we're going to take this equation, put in 10 to the 8th for our number of cycles, and calculate this yn value. Oh, we ran out of time. We're so close to... I'm going to go ahead and finish. If y'all have to go, that's okay. Times... I'm just reading the equation off of the chart here. Cycles, we have to define that. Times negative 0.0323. So that's the equation from the chart. We are going to say that we want our cycles to be 10 to the 8th. And that gives us a value for yn of 0.928. So we have that. Kr, we don't have that. That's our reliability. So there's a little chart for reliability. You know, do you want 90%, 99%, 99.99? We're going to go with 99% reliability that corresponds to 1. But you can modify this number based on how much reliability you need. Kt is one of these that doesn't have a number, it's temperature. So Kr is reliability. Kt is temperature. We don't have any reason to believe that our temperature is going to affect the performance. So we're going to leave it at 1. And at that point, we have all of the terms in here, I believe. Yes. And we end up with our factor of safety of 3.6. So we have plenty of factor of safety. We probably could have told, you know, even though this 8 KSI doesn't directly relate to a material strength that you would normally look up in a book, it still is similar enough that you can be pretty confident that 8 KSI is not going to hurt any kind of metal that we're going to deal with. But to be sure, you compare it to the Agma corrected strength. And sure enough, we have a factor of safety of 3.6. All right, next time we will get to do a similar thing, but with the contact stresses. It'll be much faster because we get to reuse a lot of these terms. We create a couple of new ones, but a lot of them get reused. So I'll post this on Moodle, this MathCAD sheet on Moodle, so you can go through it and look through it if you want to. And we'll be